Hello, my name's Madeline Norton, and today we're going to take a deep learning approach to dermatology. Skin cancer is one of the most common cancers not only in the United States, but also worldwide. Almost 10,000 people in the US alone are diagnosed with it every day. Early detection is important in order to save lives of affected patients. Computer-aided diagnostic systems, such as neural networks, can drastically aid physicians to detect skin cancer in early stages. This can also help avoid unnecessary biopsies, which helps improve patient care and reduce cost. Moreover, portable systems and even mobile apps assist both doctors and patients by providing suggested diagnoses that can act as a warning sign and lead to the early detection of malignant skin lesions. For this project, a dataset of over 10,000 skin lesion images was run through a neural network in hopes to help minimize the time and resources of medical professionals. The dataset used consisted of 7 different classifications, including melanocytic nevi, melanoma, benign keratosis-like lesions, basal cell carcinomas, actinic keratosis, vascular lesions, and dermatofibromas. Unfortunately, this data was very evenly dispersed between the classes, and as you can see in this histogram, over half the data set is made up of one single class. This can cause some serious issues when training any model, the biggest being that the accuracy will not be reading true. Whereas any given point, you can, like throwing a dart at a board, you're going to hit the NV rather than getting any of the classes. Therefore, your accuracy is automatically at 50%. To account for this, a form of data augmentation was run on the images in order to boost each of the other classes. To do this, each of the images from each class is transformed in random combinations, including rotations, tints, and crops. As can be seen in this image, we can make several different images just from one single one. After many iterations on many of the images on each of the classes, we see we have much more even classes, and also this resulted in a more robust data set. Okay, as mentioned before, this data was then dumped into a convolutional neural network and then stirred until the classification started to look correct. Well, actually, it's a little more complicated than that. Let's look deeper into what a convolutional neural network really is. A convolutional neural network is a deep learning algorithm which can take in an input image, assign importance via learnable weights and biases to various aspects or objects in the image, and be able to differentiate one from the other. In this case, the network looks for certain definable differences in each of the classes. Some of the main differences would be the color patterns and shapes of the lesions. Structurally, the most important parts of a CNN, aka the parts that I can actually control, are the layers, epochs, and batches. The layers are representative of a specific aspect or object. In this case, a layer may solely be looking for the shape of a lesion. The more layers there are, the more complicated the image can be. However, too many layers, the model is then making up aspects that may not be important. This is also known as overtraining. Batches refer to the number of images that the model gets trained on at a time. Too small of a batch and not every class will be representative, but on the contrary, too large of a batch will again result in this overtraining. The epochs then refers to the number of times each batch is ran through the neural network. I built upon a convolutional neural network that I had previously designed for a similar concept. This specific one has 50 layers. This was just my baseline, wanted to see how it worked. The accuracy of this model was then determined by what we call a confusion matrix, which is a 7x7 matrix that has columns labeled as what the actual class is, and on the rows is what the model said it was. The diagonal of a matrix is then the correct classifications, and a percentage can be calculated from there. This is the accuracy plot of my very first model. As you can see, it's going up and up, but kind of bounces around. We like to see that between the train and the validation groups, which is the validation group is a small subset of the training group just before we run it on the testing, we see that they're both increasing. However, they are kind of bouncing back and forth. Okay, and so then where this also kind of hits close to home, I work at Ravalli Family Medicine. I'm a medical assistant there. We work with four doctors, and we see about 50 patients a day. And among those patients, we often see people that come in and they have various different skin lesions. So with this project, I will turn around and make some sort of a mobile app or more accessible way for this convolutional neural network to be ran. In the clinic, we do actually have something that's called Dermalite. It's a very cool type of special scope that has a really nice light on it and a zoom, so we can take really nice pictures of skin lesions. This then gets put into an iPad. The iPad can then collect the data and can be run, these images can then be run through the model. And again, this then makes it so me not having actual training of a physician, I can take a picture of a mole, I can then run it through the model, and I could say with a good amount of certainty that this is more likely to not be cancerous, or this is likely to be cancerous, which is super cool. And I would like to give a special thanks to Dr. Sullivan, who is my advisor and has helped me throughout this entire project. It's been a lot of fun. Dr. Harder-Brower for letting me bug her in the clinic and letting me use some of her data, as well as, her really fancy scope. I'd also like to thank Shirley Davidson for always debugging my code when I was super frustrated. And lastly, my roommate, Jackie Brenny, for listening to me and the amount of times that I've just had to scream.